Let us study about the design of slabs. In the design of RCC structures, we will focus on the study of solid slabs. What are solid slabs? These are generally plate-like structures which are used to provide horizontal surfaces in buildings. It is useful for movement and occupying space, and we provide it in the form of flat surfaces such as floors or ceilings. There are slabs which are provided in the uh, form of sloped surfaces also, but here we shall focus on the study of slabs in as a flat surface. Now, why we study about slabs? Immediately after the study of beams, we know the beams and slabs are the most important flexural members in buildings, and such structural elements need to follow certain conditions based on limit state method. Both of them will have design conditions in common, and we are not going to study anything new. We are just going to go through certain caudal provisions and certain means of classifying slabs and directly jump into the procedures involved in the design of slabs. Now, you see here there are generally two kinds of slab systems: beam supported slab system and wall supported slab system. Beam supported slab system, as the name suggests, they are supported by beams, as in case of framed structures. In case of wall supported slab systems, the slab is supported by walls, as in case of load bearing structures. We will have a brief discussion about both of these now. Here you can see and differentiate the two kinds of slab systems: beam supported slab system as well as the wall supported slab system. In the beam supported slab system, you see the beams interconnected along with the vertical members known as columns, and these set of members support the plate-like structure known as slab. So the slab is supported by the beams all around. But in case of wall supported slab system, you see there are load bearing walls. These walls support the slab entirely on opposite sides or all the four sides. In both these system of slabs, we can classify the slabs into two. One is a one-way slab and the other is a two-way slab. So you will find a one-way slab and two-way slab system in beam supported slab system as well as in the wall supported slab system, and we are going to study about these two types of slab systems now. First is a one-way slab. One-way slab, how do we define a one-way slab? One-way slab is generally defined based on these two conditions: the slabs which are supported only on two opposite sides. As in this figure, you see this slab is supported on opposite sides by walls, or it can be beams also. As you see, there is a slab element, this strip of slab. When you subject it to loads, this strip will bend just like a beam. So this behaves like a beam and we call it a one-way slab. Okay, so these are supported on opposite sides, so bear it in mind. You can call other types of slabs such as these slabs as one-way slabs also. And what is the situation? These slabs which are supported on all the four sides can also be called as one-way slabs, because the length of this slab is very much greater than the breadth of this slab. So you know the slab is supported on all the four sides and you have a longer span as well as a shorter span. So the longer span we designate it as L and the shorter span we designate it as B, and if the length is at least greater than twice the width, that is, if L is greater than 2 times the B value, then we call such slabs as one-way slabs. Or in short, we can say L by B is greater than 2 for one-way slabs. So slabs we call as one-way slabs if they are supported on opposite sides, or if they are supported on all the four sides, we call them one-way slabs if the length is greater than twice the width of the slab, or L by B is greater than 2. And here we must bear one thing in mind. Here we have two spans. There is a longer span as well as a shorter span. Here we had only one span because this slab is spanning in only one direction, because only the opposite sides are supported. Here it is not so. Here all the four sides are supported. So we have longer span L and shorter span B also. Here, which is the most important span? It is a shorter span that is more important, because as you apply the load, this slab element shall undergo bending, and the effect of bending is more pronounced in the shorter span rather than in the longer span. So you see, the effect of bending is very, very important in the shorter span, because the deflection or the curvature is more in case of shorter span. So we say it is always the shorter span of a one-way slab that is very, very important. So you must bear in mind that shorter span of one-way slab is of very great importance as far as its design is concerned. So for the design of one-way slabs, we use the shorter span of the slab. Now coming to the two-way slabs. Two-way slabs, as you see, they are supported on all the four sides, and not just that, the length dimension or one span is comparable to the adjacent span, or the length and the width of the slab are comparable in nature. So L is approximately equal to B, or it is, we can say, strictly speaking, we can say L by B is less than 2. So in case of one-way slabs, we said if L by B is greater than 2, then we call it one-way slab. If L by B is less than 2, then we call it two-way slabs. So thus we have already studied about the two kinds of slabs, the one-way slab as well as two-way slab, and in our curriculum we are bound to design both one-way slabs as well as two-way slabs. So you must bear in mind, one-way slab is a slab whose span is described as L by B is greater than 2, and its shorter span is very, very important for the design. But in case of two-way slabs, since both the spans are comparable in its dimension, comparable in its magnitude, L by B is less than 2. If this condition is satisfied, we call such slabs as two-way slabs, and the deflection or the curvatures, the effect of bending is comparable in both the directions, and that is why we call such slabs as two-way slabs. Coming to the design of one-way slab, what are the essential conditions to be taken care of? We know that in case of one-way slab, the shorter span is very, very important, and since we have already said that the deflection of this strip of slab in the shorter span is very, very important, we can compare such a strip to a beam, which we have already learned. So this strip of slab, the slab is a very large planar structure which is extended over large surface, and if you take only a small element like what is shown in this figure, this small element, this can be compared to a beam. Okay, and for the purpose of design, we consider only 1 meter wide strip. If that is exactly what is given here, if we consider only 1 meter wide strip, 1 meter wide strip, that is, if we say that this is a beam of width B is equal to 1000 millimeter, then we know how to design such a beam, isn't it? So we have already learned the design of beam, and we know how to design a beam. So instead of considering this as a large slab, we consider only a small strip of this slab in the form of a beam, and then we resort to the design procedures as we do in case of beams. So for this beam, the width is 1000 millimeter, and we just have to follow the remaining procedures for the design of such a beam and extend the design to the remaining portions of the slab also. So let us see how we perform it. Generally, the reinforced concrete slabs are under reinforced and singly reinforced in nature. So this should be borne in mind. Reinforced concrete slabs, always the slabs are under reinforced in nature. So at the time of design, we should ensure that XU is less than XU max. So since it is an under reinforced section, we must ensure that XU is less than XU max. And since it should satisfy a singly reinforced section, so the section should also be singly reinforced. That is what is the requirement, for which we require to satisfy which condition? Mu should be less than Mu limit. Mu should be less than Mu limit. So we must satisfy both the conditions, XU less than XU max as well as Mu less than Mu limit while we design a one-way slab. So we are talking about the design of one-way slab, where the designs should essentially satisfy the condition XU is less than XU max as well as Mu is less than Mu limit. And now how are we going to provide the reinforcements? We know this is a one-way slab and we have considered only a small 1 meter wide strip of this slab which will behave as a beam, and we design for the beam, and we can invariably determine the AST value, the tension reinforcement to be provided in such a beam, from the essential equations which we have already learned in the design of beams. So we know the value, we have determined the value of AST, the area of tension reinforcements. And how should it be provided? It should be provided like this, along the shorter span. The reinforcements should be provided, the tension reinforcements should be provided along the shorter span, and such reinforcements we call it as main bars. So in one-way slabs, once you determine the AST value, the AST, the tension reinforcements, should be provided along the shorter span, and such reinforcements we call it main bars or main reinforcements. Unlike in case of beams, the AST which we provide, we have determined for 1 meter wide, we will extend it to the other regions of the slab also. So whatever AST you have determined for this 1 meter wide strip, you have to provide it on the other sides of the slab also. That is exactly how we design, and for which case you need to determine the spacing between these two bars. So the adjacent bars are spaced by, are distanced by some amount, and we have to determine what is the distance between the adjacent bars, and for which we define the term S, which is the center to center distance or spacing of bars in millimeter. So what is the spacing between the adjacent bars? Since S is the spacing between bars, and we have 1 meter wide strip of a beam, 1 meter wide beam, and in order to find the number of bars, if we know S and we know the width of this beam, we just have to divide the width of the beam by the spacing between two bars to get the number of bars. So once we determine the number of bars, which is equal to 1000 divided by S, we want to find what is S. There are other ways to find the number of bars also. If you know the AST value for this section, you can determine AB. What is AB? AB is the sectional area of one reinforcement, one bar or one reinforcement. If you know the diameter of the bar, let us say phi is the diameter of the bar, then phi square by 4 will give the cross sectional area of one reinforcement. So that is what is given by AB, area of one bar. A suffix B gives the area of one bar. And what is AST? You know the area of tension steel to be provided in this 1 meter wide strip of beam, and by dividing AST by AB, you will get the number of bars. So you have already determined the number of bars as 1000 by S. Here you are again determining the number of bars as AST divided by AB. So you just equate both the terms. 1000 by S is equal to AST divided by AB, from which you can say spacing S is equal to 1000 into AB by AST. Here you need to keep in mind that the spacing S is expressed in millimeter. S is in millimeter. So everything else should also be expressed in millimeter. Okay. So in order to determine the spacing, if you know the cross-sectional area of one bar and you determine AST for this 1 meter wide strip of beam, then you can easily determine the spacing. S is equal to 1000 into AB by AST. Now you have already provided the main bars. Now we have to provide what are called distribution bars. So we have already provided main bars. Main bars are provided in the tension zone of the slab, and that is not just enough. Distribution bars should also be provided. So what are distribution bars? Distribution bars are reinforcements provided in the direction perpendicular to the main bars. So the bars which you provide perpendicular to the main bars on top of it. So main bars are occupied at the bottom, and just on top of the main bars you place the distribution bars. Why? We call distribution bars as secondary reinforcements, or distribution bars, or distributors, or temperature reinforcements. Distribution bars are provided for different reasons. What are they? The portion of the section above the neutral axis is under compression and hence subjected to lateral expansion due to Poisson effect. So what does it mean? See this figure. This is a figure which shows what is known as Poisson effect. You know, this is a beam. This is a 1 meter wide strip of beam in a slab. Okay, and when you subject it to loads, what happens? The beam bends, and the region above the neutral axis will be subjected to compression as shown in this figure, and the region below the neutral axis will be subjected to tension as shown in this figure. Now what happens when you compress a solid structure or structural element? When you compress it in this direction, it will have a tendency to expand in the lateral direction. Sideways expansion is possible if you provide compressive force in the longitudinal direction. If you provide compression in this direction, you will experience expansion in the sideways direction or the lateral direction. Similarly, the region below the neutral axis, if you observe, you apply tensile force, it results in sideways compression or contraction, lateral contraction of the structural element. Okay, you know, this is a continuous slab where this is just 1 meter width, and when you subject it to external loads, such compressions occur, and as a result lateral expansions and contractions occur. As a result of these lateral expansions and contractions, we have materials on the adjacent edges of these elements. This 1 meter wide strip, on the sides of these elements you have slab. This is a continuous slab where you are taking just 1 meter strip. Okay, so due to the materials on the adjacent edges of the element, this lateral expansion and contraction will be heavily hindered, will be heavily restricted. So as a result of this restriction imposed on the lateral expansion, secondary moments or secondary stresses shall develop. Other kind of stresses or other kind of moments, we call them secondary moments and secondary stresses, develop in slabs. Okay, so such kind of stresses are not good for the slab, and to resist its effect we should provide reinforcements in the direction perpendicular to the main bars, and we call them distribution bars. We call them secondary reinforcement. That is exactly why we call them secondary reinforcements, because they are meant to resist the secondary stresses in the slabs. Okay, the secondary stresses imposed due to Poisson effect, this lateral expansion and contraction, we call them Poisson effect. You know about Poisson ratio. So Poisson ratio, just like that, we have Poisson effect, where lateral expansion and contraction is known as the occurrence of which is known as the Poisson effect, and as a result of this Poisson effect, the lateral expansion and contraction shall be hindered or restricted by the adjacent slab material on its sides, and as a result stresses develop, and we call such stresses as secondary stresses or secondary moments, and we need reinforcements to resist such effects, and there we provide secondary reinforcements. Okay, there are other reasons also to why we provide distribution bars. For example, you apply some loads on the slabs. Very heavy loads, if they are applied on the slabs, can result in local stress development which may not be as you predict. To distribute such loads to the main bars, you need some distribution bars. So that is exactly why we call them distribution bars. To distribute the local stresses and secondary stresses developed due to heavy loads applying on the slabs, we need some means to distribute such loads to the main bars, and we call them distribution bars. Okay, and further there are reasons too. These distribution bars will be used to resist the effect of temperature as well as shrinkage in slabs. So as you know, due to change in temperature in the field conditions, the slabs can expand or contract, and as a result stresses may develop, and to resist such stresses we need reinforcements, and these distribution bars will further serve as temperature reinforcements to resist such stresses. The stresses induced due to shrinkage of concrete will also be resisted with the help of secondary reinforcements. Now we move on to the caudal provisions for the design. We know that the design of one-way slabs is merely like a design of a singly reinforced beam, and you need to observe certain additional conditions provided in the code, and we will just have a look at what it is. So from page number 39 of IS 456, you have entirely a different clause and section for solid slabs itself, that is clause number 24, and there it is written the provisions of 23.2 for beams applied to slabs. And what does it say? What is this 23.2? We have already had a discussion about this in the design of beams, where we had to restrict the span to effective depth ratios in beams. The same is applied to slabs as well. For cantilevers, what is the effective span to effective depth ratio? What is the maximum value of effective span to effective depth ratio? It is 7. For simply supported beams it is 20, and for continuous beams it is 26. We already had a discussion about this. So the same can be applied in case of slabs also. For simply supported slabs and for cantilever slabs and continuous slabs, corresponding values of effective span to effective depth ratios may be obtained from the Indian Standard Code. Note number 1 is given as for slabs spanning in two directions, the shorter of the two spans should be used for calculating the span to effective depth ratios. So in case of one-way slabs, we are concerned only about the shorter span, where the shorter span is used to calculate the effective span to effective depth ratio. We know that slab is a structural element which is very thin compared to beams. It has large expanse, it occupies large surface, but its thickness is very small compared to beams. So the effect of this ratio, the effective span to effective depth ratio, is very important. We have to restrict the deflections in slabs very much more than what we have done in case of beams. We are very much concerned about the deflections in slabs because it is very thin structural element, and the structural element, if it becomes very thin due to the application of loads, it can deflect and bend very much, unlike in case of beams. So we have to determine the effective span to effective depth ratio very accurately. How? So as we already discussed in page number 37, the limiting values of effective span to effective depth ratios are given, but we have additional provisions in 23.2.1 the subclause C, depending upon the area and the stress of steel for tension reinforcement, the values in subclause A or B shall be modified by multiplying with the modification factors obtained as per figure 4. And the figure 4 is also given alongside. In page number 38 it is given. You see, in case of slabs, it is not just enough you restrict the effective span to effective depth ratios to these values. You have to modify these values suitably to fit the case of slabs, for which you need to follow this additional condition also, by which you can determine the modification factors. So how do you determine the modification factor? You have to modify these values and you need modification factors, and the modification factors you will obtain from figure 4. Okay. The figure 4 talks about the percentage tension reinforcement on x-axis and the modification factor on the y-axis. By knowing the suitable values of Fs, what is Fs? Fs is the stress in steel. Which steel? Tension steel. So what is the stress in the steel at service loads? So approximately the equation for Fs is given here. So you just have to determine the value of Fs from this equation. Fs is equal to 0.58 Fy into area of cross section of the steel required divided by the area of cross section of steel provided. And you can actually neglect this term. This is the area of cross section of the steel required and area of the cross section of the steel provided. So since at the beginning of the design you don't know these values, you can neglect this term. You can approximate them to be equal, and these numerator and denominator gets cancelled off, and you just have to focus on this value 0.58 into Fy. Okay, so Fs can be approximated as 0.58 times Fy. So what you should do to get the modification factor at the beginning of design? So at the preliminary stage, this is again figure number 4. You see, at the preliminary stage of design, you need to have the modification factor, but you don't know the percentage tension reinforcement. So for that case, you can make certain assumptions. And how do you perform it? You see the graphs, there are several curves provided in this graph. Fs is equal to 290, Fs is equal to 240, Fs is equal to 190, 145 and 120. Okay, these are all in Newton per millimeter square. If you know the grade of steel, let us say the grade of steel is Fe415, you can find what is the corresponding Fs value for Fe415. How? Just have to substitute it here. 0.58 times Fy. Into this term, I have said that you may neglect it for the time being. This term can be taken as equal to 1. So we are left with this terms only. 0.58 into Fy. 0.58 into what is Fy? It is 415. If you substitute it here, you get Fs is equal to 240 Newton per millimeter square. So this curve for Fs is equal to 240 corresponds to Fe415. So this is the curve which follows Fe415. Now coming to Fe500 grade, just substitute Fy is equal to Fe500 and you get Fs is equal to 290 Newton per millimeter square. So this curve for 290 represents the curve for Fe500 grade steel. And you just have these two curves, one for Fe500 and one for Fe415, and you need to determine the modification factors accordingly. At the beginning of the design, you don't know the percentage tension reinforcement provided in the slab, so you can generally make an assumption that is percentage tension steel used in slabs is approximately 0.2 to 0.6 percentage. So this is from experiences and different experiments which we have obtained this range of value. 0.2 to 0.6 may be generally assumed as the percentage tension reinforcement used in slabs. And corresponding values of modification factors you can get for Fe415 and Fe500 grade steel, the corresponding curves for which, and you can say approximately the range of the modification factors, it varies from about 0.9 to 1.6, And for the preliminary design purpose, you can take the modification factor for the tension reinforcement as equal to 1.25. So bear it in mind, the effective span to effective depth ratio, once you obtain it, you have to multiply it with this modification factor in case of slabs. So for slabs, you should remember that the modification factor of 1.25 should be multiplied with the effective span to effective depth limiting ratios to obtain the correct values. Okay, so from these, you know the effective span to effective depth ratio limiting value and multiply it with the modification factor 1.25 and correspondingly find the effective depth, and procedures shall follow thereafter as in case of beams. Now we are left with few caudal provisions. These are also to be kept in mind. Please note the page numbers. The maximum distance between bars in tension. So the main bars provided, the main reinforcement as well as the distribution reinforcements provided in the slabs should be separated by a spacing, and this spacing shall be well within the limits prescribed by the IS code. And what are they? So it is given in page number 46 that for horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth of the solid slab, or 300 mm, whichever is smaller. So the spacing, the center to center spacing between the main bars is what is given. It should not exceed 3 times the effective depth of the solid slab, that is 3D or 300 mm, whichever is smaller. The smaller of the two, 3D or 300 mm, you have to determine. And the spacing which you obtained, we have already obtained the spacing here as S is equal to 1000 into AB by AST, and this value which you get here, this value which you obtain here should conform to this specification. That is, it should be less than 3D or 300 mm. Recommendation for spacing for temperature reinforcements or distribution bars here. It shall not be more than 5 times the effective depth of a solid slab, or 450 mm, whichever is small. So earlier case was 3D or 300 mm. Here the distribution bars should be spaced less than 5D or 450 mm. So this is 3D or 300 mm. This is 5D or 450 mm, whichever is smaller. Okay. Now we are left with determining the minimum AST minimum. So it is given in page number 48. For HYSD bars or FE 415 or FE 500 grade steel reinforcements, the minimum reinforcement to be provided is 0.12% of the cross-sectional area, the gross area. Okay. What is the maximum diameter of the bar? Reinforcing bar maximum diameter to be followed is 1/8 of the total slab thickness. 1/8 times the total slab thickness.